Let's talk strategies for approaching metabolic accounting problems, where you're given two molecules and you're asked to say how many NTP, so like ATP, GTP, you would need or you would generate in order to interconvert those molecules, as well as things like how many NADH, FADH2 you would generate directly, as well as how many you could get from oxidative phosphorylation. These questions can seem kind of intimidating, but they're really not that bad. So let's go through step by step how you can approach them. First, you want to identify the starting point. So what molecule are you starting at and how many carbons does it have? Next, you want to identify the ending point and how many carbons it has. Trace the path between them and follow that path, noting when and where you generate or use those various molecules, your NADH, your FADH2, your NTPs. Then what you want to do is make sure you accounted for all the carbons. If you didn't account for all the carbons, then some of the steps you're actually going to have to do twice. This is especially important to think about because in glycolysis, you go from a 6-carbon molecule of glucose into two 3-carbon molecules. And then everything that happens once you do that split at the aldolase step, all this stuff is going to happen twice. So if you're doing something down here and you're thinking in terms of glucose, all this is going to be happening twice. And same with the citric acid cycle, because if you take that pyruvate from glucose, from glycolysis into the citric acid cycle, well, you actually get two pyruvates from glycolysis, and so you need to take this into account. The number of carbons also comes into play when we're thinking about the citric acid cycle, because you lose 2 carbons per turn of the cycle. You can enter the cycle at various places, leave at various places, and you need to make sure that you're accounting for all the carbons. So if you stick something into the cycle that's say 5 carbons, you're actually going to need to go around the cycle about 2.5 times in order to make it so that you get rid of all those carbons. And depending on where you kind of come in, you're going to generate different amounts of things. So you want to keep track of where these kind of key points are that you're generating the things that you're trying to keep track of. And then at the end of the day, you need to sum things up and see where things lay. So let's do some practice problems. So let's start with the TCA. So the citric acid cycle, tricarboxylic acid cycle, Krebs cycle, whatever you want to call it. It's really awesome. And it's like this roundabout. And so you can put things in at various places and you can take things out of various places. But if you think about going just one full turn of the cycle, where you take oxaloacetate and you bring in 2 carbons from acetyl-CoA, you join those up with oxaloacetate's 4 carbons, you get the 6-carbon citrate. You go around the cycle, you lose 1 carbon, you lose the 2nd carbon. You also lose 1, 2, 3 NADH, 1 FADH2, and you gain 1 NTP. So it's a GTP or an ATP, depending on the isoform. And so that's for a full cycle, you would get that. But you don't always do a full cycle, and sometimes you do multiple cycles. So let's go through a practice problem to show what I mean. Again, you can kind of think about things in simplified terms. You want to think about those key places. For each turn of the cycle, you get those 2 carbon dioxides, 3 NADH, 1 FADH2, and 1 NTP. But that's only if you're going all the way around the cycle. And so if you're going from here to here, or if you're going from here to here, or here to here, you have to think about what are you actually generating in the reactions that you're going through. And so you're going to have to track which reactions you're actually going through. So again, we're going to follow that strategy. And so we're going to take that practice problem, we're going to identify our starting point and the number of carbons it has, the end and the number of carbons it has, trace the path between them, follow that path, noting where we're generating those things or using those things, and then we're going to make sure we accounted for all the carbons. If not, we'll repeat the parts that we need to repeat, sum things up, and voila. And of course, make sure our answer makes sense. So first question, how many NADH, FADH2, and NTPs are produced directly from completely oxidizing alpha-ketoglutarate and resetting the TCA? So first step, identify the start and how many carbons it contains. So we're dealing with alpha-ketoglutarate and it has 5 carbons. If we don't remember offhand, alpha-ketoglutarate has 5 carbons. Well, if we can remember, pyruvate has 3, acetyl-CoA has 2, oxaloacetate is 4, then we make citrate, which has 6. And then you lose 2 carbons each turn around. And at this point, you've lost 1 carbon. And so now you would have had 6 minus 1 is 5. So alpha-ketoglutarate has 5 carbons. So we have 5 carbons. And our destination, we want to get first to oxaloacetate so that we reset the cycle. We'll start that way. And the oxaloacetate has 4 carbons. But that would only get rid of 1 carbon. If we were only to go straight from here to here, we would only be getting rid of 1 carbon. If we want to completely oxidize alpha-ketoglutarate, that means we need to get rid of 5 carbons. And this is only going to get one of 1 carbon. Now we're going to get to 4 carbons, and to get rid of 4 carbons, we're going to need to go 2 full turns of the cycle. So in order to remove 5 carbons, we're going to have to do 2 full cycles and 1 partial cycle, since we remove 2 carbons each cycle. And now we're just going to track these. So from our partial cycle, we're starting at this alpha-ketoglutarate, going to oxaloacetate. As we do so, we're going to generate 2 NADH, 1 FADH2, and 1 GTP. Now we're back at oxaloacetate, and so we're going to go around the cycle, lose 2 carbons. Along the way, we're generating 3 NADH, 1 FADH2, 1 GTP. We also lost 2 more carbons, so we've lost 3 carbons at this point. We need to lose 5, so we need to go around the cycle again. We're going to generate the same amount of stuff from the second turn. And so at the end of the day, we're going to generate 8 NADH, 3 FADH2, and 3 GTP. We had to go around the cycle about 2.5 times, but you can't just divide the last turn by half, because say we started at succinate, we would have missed out on generating this NADH, and we would have missed out on generating this GTP. So we need to think of it more as a partial cycle than half a cycle, because which partial part you have is going to matter. And so in this case, we are coming in here, so we missed out on this NADH, but we got this NADH. If we had joined in at citrate, then we would have gotten another NADH. So it's really important to think about where you're starting and where you're ending. And the only place that's going to really come into play is in that partial cycle. Once you get to the full cycles, you can actually simplify things and think about how many full cycles you need. And remember that each full cycle, you're generating 3 NADH, 1 FADH2, and 1 GTP. No matter how you do it, you're going to end up with 8 NADH, 3 FADH2, and 3 GTP. And that was just directly from the citric acid cycle. What if you were to think about if we took those through the electron transport chain and oxidative phosphorylation? How many ATP could we generate in total? Remember, for each NADH that you're generating, you're going to generate 2.5 ATP, because you can pump 10 protons, so you need 4 protons per ATP. So that'll give you 2.5 ATP per NADH on average. With your FADH2 here coming in at complex 2, you miss complex 1 where you pump protons. And remember too, complex 2 is your succinate dehydrogenase of your citric acid cycle. So this is your complex 2 that's right here, ready to go and pass those electrons to Q, but it's not going to pump protons. And so you're only going to pump out the 6 protons. 6 divided by 4 is going to be 1.5. So you get about 1.5 ATP per FADH2. Do the math. We have 8 NADH times 2.5 ATP per NADH, 20 ATP. From our FADH2, we're going to get 4.5. Then we get 3 GTP directly. And we add that up and we get 27.5 ATP. Not too shabby. Now let's do another example. In this case, we're not starting with something that's already in the cycle. Instead, we're starting with something that's outside of the cycle. And we need to think about how we bring it into the cycle as well as then its path through the cycle. In this case, we are being asked about alanine. And so the question is, how many redox reactions would be required to completely oxidize 1 molecule of alanine? And again, this is going to incorporate the resetting of the TCA, so getting back to oxaloacetate. We're being asked to show our work by naming the enzymatic steps by enzyme name. And if the same enzymatic step happens twice, we'll count it as 2 reactions. But are things going to happen twice? Let's think about this. We need to think about our start point and our end point. Alanine is up here. Alanine has 3 carbons. And alanine can be converted to pyruvate just by transamination. So we just take the amino group off of alanine, we stick it onto alpha-ketoglutarate to give us glutamate. And we're left with pyruvate. And so we can see we're not losing any carbons here. And so if we can remember that pyruvate has 3 carbons, we can remember that alanine has 3 carbons to get rid of. And so now we're at pyruvate. And we need to get all the way to oxaloacetate. But we know how to go from pyruvate to oxaloacetate. And so we could totally do this. You might think, like, okay, let's just go straight from pyruvate to oxaloacetate with pyruvate carboxylase, but that has the opposite effect of what we want. In that case, we would be actually adding a carbon, where instead we want to remove the carbons. We want to oxidize the carbons of alanine. So we want to go through the pyruvate dehydrogenase step to acetyl-CoA, take that through the citric acid cycle to give us oxaloacetate, and losing the carbons along the way. We need to lose 3 carbons, but remember that even though we only lose 2 carbons per turn of the TCA, we lose one of the carbons in the pyruvate dehydrogenase step in the generation of the acetyl-CoA. So let's actually go and track this out. If we want to think about redox reactions, we need to look for those reactions that are generating the NADH, the FADH2, the NADPH, those sorts of things, or using those. So if we're generating them, then those are going to be our oxidation reactions if we're like generating NADH. And if we're using NADH, that would be a reduction reaction. In this case, when we're doing catabolism, we're typically oxidizing things. And so we were going to be looking for the generation of the NADH and the FADH2 in this case. And so our first case where we're going to see that is the pyruvate dehydrogenase. So we're going to track this through. We go from alanine to pyruvate to acetyl-CoA. Note that we have arrows going in and here, and it looks like we're going some sort of redox, but that's the side pathway. And so this is how we can get lactate into form pyruvate, but we're starting from alanine. We're not starting from lactate, so we can just ignore this and follow the arrows directly from alanine to pyruvate through pyruvate dehydrogenase. Now we get our acetyl-CoA. We follow this around. We get to isocitrate dehydrogenase. We're generating NADH. We've got a redox reaction. So now we've had 1, 2. We get another redox reaction. We can see we have another NADH generated by alpha-ketoglutarate dehydrogenase step. So that's 1, 2, 3. We have another one. We go around here. We see the succinate dehydrogenase. We're generating FADH2. So that's our 4th. And now we have number 5. When we're going from malate to oxaloacetate, we're generating another NADH. So we have 5 redox reactions in the process of catabolizing the alanine carbons. And we could also think about, what did we generate directly? Well, we generated 1 NADH here, and then we get 3 in the cycle, so it's 4 NADH. We also generated 1 FADH2 and 1 GTP. And if we include oxphos, we do the math like we did before, so we multiply each NADH by 2.5, each FADH2 by 1.5, and then we take into account what we had generated directly, and we end up seeing that we can get 12.5 potential ATP. So this is a lot less than that 27.5 we got from alpha-ketoglutarate, which say we could have gotten from glutamate, but we were starting with 3 carbons instead of alpha-ketoglutarate, which started with 5. And so this makes sense that we're generating less energy. Speaking of glutamate, so glutamate can be converted to alpha-ketoglutarate in order to do the cycle. We saw up here that when we took the nitrogens off of alanine and stuck them onto alpha-ketoglutarate, we got glutamate. And go the other way, we can stick the amino group from glutamate onto an alpha-keto acid to give us amino acid. And so this is a way that we could actually take glutamate and we can make alpha-ketoglutarate. If we do this, we're then adding these carbons into the cycle. So glutamate can be converted to alpha-ketoglutarate by a variety of transaminases. Are such reactions anaplerotic to the TCA? Yes, so alpha-ketoglutarate is a 5-carbon component of the TCA, and this reaction replenishes it. So if we were to go and say take out malate to go and make glucose, what we could do is then we could add back in carbons by this reaction, converting the carbons of glutamate into alpha-ketoglutarate, which can be in this pathway. So if we remove something from the pathway, we need to add something into the pathway in order to regenerate the oxaloacetate so that another acetyl-CoA can come in. So acetyl-CoA can't come in unless there's already oxaloacetate present. And if you take out anything along this way and you don't add back carbons in more than the acetyl-CoA, you don't add back the 4 carbons or more, then you're not going to have the oxaloacetate. If you don't have the oxaloacetate, you can't bring in acetyl-CoA. Speaking of glucose, is glutamate glucogenic? So yes, because glutamate can be metabolized to alpha-ketoglutarate, which can enter the TCA, be converted to malate, taken out of the mitochondria and used to make glucose, without depleting carbons from the TCA, we can say that glutamate is glucogenic. How about acetyl-CoA? Could 2 molecules of acetyl-CoA be used to go turn around the TCA? Each molecule of acetyl-CoA has 2 carbons, but this is a no. You need oxaloacetate to join to. And if you can't make oxaloacetate or any TCA intermediate that can be used to make oxaloacetate from acetyl-CoA, then you can't bring in acetyl-CoA. So just acetyl-CoA alone won't do it, which is why if we have certain molecules like certain amino acids that can be broken down only into something like acetyl-CoA, we call those ketogenic, but not glucogenic, because the acetyl-CoA cannot enter the pathway unless you have oxaloacetate there. And so if you take malate out to make glucose, you don't have oxaloacetate there. And if you don't have oxaloacetate there, then your acetyl-CoA can't come in. But what about pyruvate? Say we had 2 molecules of pyruvate. Could we go around the 2CA? And so the answer for this one is yes. We saw we take pyruvate, we can use pyruvate dehydrogenase in order to remove a carbon to give us acetyl-CoA. But we just said that acetyl-CoA can't come into the pathway unless oxaloacetate is there. Can we make oxaloacetate from pyruvate? Yes, we can. We use this different enzyme, pyruvate carboxylase, which actually adds that carbon onto pyruvate to give us oxaloacetate. So here we were removing a carbon to give us acetyl-CoA. Here we're adding a carbon to give us oxaloacetate. And so in this way, we're able to generate the 2-carbon and the 4-carbon that we can join up to make our citrate. And so we use 1 of the molecules of pyruvate to generate acetyl-CoA, 1 to generate oxaloacetate. We join these together through citrate synthase to make citrate, and we go around our cycle. Are either of those reactions anaplerotic? And if yes, which? Well, the one that's anaplerotic is the one that's actually going to be replenishing the pathway intermediates. So the anaplerotic reaction is going to be the pyruvate carboxylase, where we're adding a carbon to pyruvate to give us oxaloacetate. And the oxaloacetate is in the pathway, and so this is going to be an anaplerotic reaction that's replenishing the pathway intermediates. So that pyruvate carboxylase step is an example of an anaplerotic reaction. Getting back to glucose, how many NTPs, so ATP, GTP, etc., can we get directly from completely oxidizing glucose? And so again, it's really important that we think about our numbers of carbons. And so if we think about glucose, we have 6 carbons. And we need to remember that at the aldolase step of glycolysis, we're going to split into 2 3-carbon compounds. And then everything that happens after that is going to have to be repeated twice. So let's think about where we're starting, where we're ending, trace the path between them, follow that path, account for our carbons, sum things up, and check and see if it makes sense. So if we think about glycolysis, well, we start with that 6-carbon glucose. We go down the pathway, and we want to look and see where are we generating the ATPs or using ATPs. And so we can see that in glycolysis, we're going to be using ATPs, 2 ATPs at the 6-carbon step, but then generating 2 ATPs at the 3-carbon step. And because everything in this 3-carbon step is going to be repeated twice, we're going to be doing 2 times 2 ATP minus 2 ATP, and 2 times NADH, which we'll take into account later. But basically, because we're repeating these steps twice, and we have the ATP that's generated in this 3-carbon step right here and right here, so we get 2 times 2 ATP is going to be 4 ATP. But then we were actually using 2 ATP in these 6-carbon steps. And so those ones we don't have to multiply because we're doing these only once. So we lose 2, but then we gain 2 times 2. So we gain 4, lose 2. Overall, we gain 2 ATP. But that was just from the glycolysis part. And now we have that pyruvate at the end of glycolysis. We actually have 2 molecules of pyruvate at the end of glycolysis. And we can take those pyruvates into the citric acid cycle. And in that citric acid cycle, we're going to be generating the GTP or the ATP. So we're generating the NTP, and we're doing this twice. So we have 2 times 1 NTP, and so we get 2 NTPs. So we get 2 NTPs from the citric acid cycle, 2 from glycolysis. We have 4 overall, just directly from the oxidation of glucose. Note that we had the pyruvate dehydrogenase step in between the pyruvate and the citric acid cycle. However, we did not generate any NTPs in that step. But we do generate an NADH. And so now let's think about how many NADH and FADH2 we could get directly from completely oxidizing the glucose. So again, we need to take into account that at this 3-carbon step, everything is repeated twice. So we're going to have 2 times this generation of the NADH here. And we're going to have 2 times the generation of the NADHs and the FADH2s of our citric acid cycle. We're also going to have 2 times the NADH generated by our pyruvate dehydrogenase step. So all of this is happening twice. All of this is happening twice. This was happening just once, but we didn't have any of these NADH or FADH2 in this part that was happening once. So everything we're going to be considering now is going to be happening in the step at which we're doubling everything. So in glycolysis, we're going to get 2 NADH because we're going to be multiplying that 1 NADH we get from the glyceraldehyde 3-phosphate dehydrogenase step by 2. We're going to be getting 2 from the pyruvate oxidative decarboxylation because, again, we're going to be multiplying 2 times the pyruvate dehydrogenase step. In our citric acid cycle, remember for each turn, we were generating the 3 NADH and 1 FADH2. And so we multiply that by 2, we get 6 NADH and 2 FADH2. Okay, so now let's think about what can we do with those electron carriers. So remember, we're passing the electrons from our fuels, from that glucose, onto those electron carriers. And so the electron carriers can take them through the electron transport chain, use the energy from the electron pass-offs, those favorable redox reactions, to power the pumping of protons to make a proton gradient that can be used to drive the generation of ATP. So again, we just kind of do the math. So we saw we had 10 NADH and 2 FADH2. We multiply those by 2.5 and 1.5, and we see that we generate 28 ATP, or that's kind of like the maximum we could generate if this is completely efficient. Now let's take into account the NTPs that we generated directly and those ones that we got from the oxphos. So we had the 28 from the oxphos, and then we had the 4 that we generated directly. So that is where we get that we can kind of get a maximum of 32 ATP. And we saw that most of the ATP that was generated comes from the oxphos, not from glycolysis, which is why if you have mitochondria, if you have a functioning electron transport chain, you've got oxygen, all this stuff, you're going to want to do that route in order to get the most energy as opposed to anaerobic glycolysis. But if you're in a scenario where you can't do the oxidative phosphorylation, if your electron transport chain's backed up, if you don't have oxygen, if your citric acid cycle is not running then, if you don't have a mitochondria because you're a red blood cell, all these different situations in which you can't do this oxidative phosphorylation, then the anaerobic glycolysis, where we're making lactate instead of regenerating the NAD plus this way, we're regenerating the NAD plus by making lactate. That gives us a way to keep glycolysis going. Now let's think about going the other way. How many NTPs are required on net to make one molecule of fructose 6-phosphate from pyruvate? Show your work and identify by enzyme name the steps at which NTPs are used. So again, we can use the same strategy where we identify our start point and number of carbons, the end point and number of carbons, trace the path between them, follow the path, noting when and where we generate or use NADPH, FADH2, ATP. Make sure that we accounted for all the carbons. If not, repeat the steps as needed and sum things up and see if it makes sense. So we want to identify our start and our stop. Our start point is pyruvate, which is 3 carbons, and our end point is fructose 6-phosphate, which is 6 carbons. So just like we saw with glycolysis, we're going to have to be doing all these 3 carbon steps twice. But this is showing us glycolysis and not gluconeogenesis. The reactions that are shared, these ones that have these reversible arrows, these are the shared reactions. So in this step, say we'd be losing an NADH, and in this step, we'd be losing an ATP. But this step was an irreversible arrow, and so we'll see we're actually going to need 2 NTPs to go the other direction. So if we look at the context of gluconeogenesis, we're starting at pyruvate, 3 carbons, going to fructose 6-phosphate, 6 carbons. Along the way, we want to look and see where are the reactions where we're going to be using the ATPs or the GTPs or whatever. And so in this case, what we're doing is we're going to be using one at this pyruvate carboxylase step, another at this pep carboxykinase step, another at this phosphoglycerate kinase step. And so those would be 3, and then we're doing all this twice, so that would be 6. So 6 NTPs. You might be thinking, okay, well, why aren't we generating an ATP here and generating an ATP here? And the reason why we're not is because we're not doing those reactions. And so those are the irreversible steps where in glycolysis, you're using the ATP to phosphorylate the compound, the glucose, say here, to give glucose 6-phosphate. To go the reverse way, you're actually using glucose 6-phosphatase to just take water and hydrolyze off that phosphate group. So you're not trying to stick the phosphate group back onto ADP to give us ATP. Instead, you're just cutting that phosphate group off. So you're not going to be generating an ATP here. And so all we need to worry about is these 3. Then each of those is going to be happening twice because pyruvate's 3 carbons. And then we need to get to the 6-carbon compound. So we need to do all this twice. So 2 times 3 is going to be 6. So we need 6 NTPs. Also, we can see that the question didn't ask us, but we can also see that we're basically going to be using 1 NADH in this glyceraldehyde 3-phosphate dehydrogenase step. What if the question had asked us about glucose? Well, the answer would actually be the same. Because to get from fructose 6-phosphate to glucose, we weren't going to be using NTPs. And so remember that these ones are just getting hydrolyzed off in this direction, so we don't need to worry about these. And so all we need to worry about is these steps, and these steps were the same for the fructose 6-phosphate. And so for the answer for glucose will be the same. We are going to basically be using 6 NTPs and 1 NADH. But again, it's going to ask us about the NADH step. But we can see that in gluconeogenesis, to make glucose from pyruvate, we're actually going to be needing to use 6 NTPs, even though to go from glucose to pyruvate, we were generating 4 NTPs directly. And then we had all that energy that we could take in the form of those electron carriers to cash in later for ATP, as well as take the pyruvate through the citric acid cycle to get energy that way. And so even though gluconeogenesis is thermodynamically favorable overall, we are having to spend a lot of energy in the form of these NTPs in order to make glucose from pyruvate. And then we need to remember that in most of your tissues, other than your liver and your kidneys, you're not actually able to go all the way to glucose because most of your tissues don't have this glucose 6-phosphatase. So your tissues might be able to go to, say, glucose 6-phosphate, and then they could use that for themselves for various pathways, like in your muscles, glycogen storage, or the pentose phosphate pathway in various tissues. But you can't actually let it out into the bloodstream if you don't have glucose 6-phosphatase, which is why your liver and your kidneys are the only ones that can kind of, or main ones that can kind of do gluconeogenesis in its entirety because they have that glucose 6-phosphatase. They can be benevolent and actually let the glucose out. But that got kind of off track. Speaking of tracks, let's think back to our strategy. So no matter what problem you're approached with, identify the starting point and number of carbons, identify the ending point and number of carbons. If you can't remember how many carbons something has, try to find a molecule in the pathway that you know how many carbons it has. So if you can remember, glucose has 6, pyruvate has 3. Then think about, are you losing any carbons in between them and that sort of thing. Trace the path between them, follow that path, noting when and where you generate or use NADH, FADH2, NTP. Make sure you accounted for all the carbons. If not, repeat the steps as needed. Remember that for each turn of the cycle, say, you're going to be losing 2 carbons. And so if you have a molecule in there that you need, or you're bringing in a molecule in there that you want to remove carbons from, you're going to need 1 turn of the cycle per 2 carbons. But you might also have to do a partial cycle. So you need to think about where exactly you're coming in and coming out. Because even if you're coming in with 4 carbons, it might not be exactly 2 turns of the cycle. You might need to do a partial turn. And in that partial turn, you might be, say, generating FADH2 or generating NADH. So it's not just enough to think about the number of carbons. You need to actually think about the position in the pathway and trace the path of that molecule as it goes and interconverse between the molecules. Sum things up, make sure it makes sense, and pat yourself on the back.